I know that this is a late session, and thanks for attending. Thanks for being patient. My name is Devi Prasad, and for the next half an hour or so, I'll be talking about some of the cryptographic details of the signal protocol. So this talk is kind of exploratory in the sense I have a gigantic slide which is uploaded on the site. I removed a few of those slides and watered it down, but then still it has more slides than perhaps I can handle. So you're free to interrupt me in the middle if you have any questions. So many do not know that Signal is the foundational protocol for WhatsApp, Skype, and even Google messaging app. So some of the core cryptographic end-to-end encryption sub-protocol in WhatsApp is handled by Signal protocol. So Signal is a foundation that implements the Signal protocol and many other sub-protocols which work in the server and the famous end-to-end encryption thing. So it's very interesting to study Signal by itself because it becomes a core of many other protocols. So as the mission of Signal says, it tries to protect free expression at any cost. So we'll see what are those costs, what is involved, what engineering is involved, what are the challenges that Signal protocol faces and tries to solve, right? Protecting free expression is not easy, as Signal's blog says many countries ban Signal, so people are not able to use Signal app as such in those countries. And there is no way to circumvent regulatory restrictions that are put on those things. So, and then yet, because Signal is open source, free, it is run by a foundation, there are costs of running this software. So in one of the blogs, it is mentioned that their cost of running their servers by 2025 is around $50 million US. So protecting free expression is expensive. So naturally the question comes, why should we study Signal, right? This is kind of a study of the Signal protocol. It's interesting. There are many in the core parts of Signal protocol, there are many cryptographic primitives and then constructions of sub-protocols that are quite interesting intellectually and in engineering also. So my interest is basically in trying to see the software, the implementation part of it, and then trying to understand the cryptographic primitives, the math behind it, and so on. So the slide deck, my slide deck has there are only 2 or 3 slides that have math. I've tried to remove the math as much as possible, but still I could not, completely avoid. And that is very simple math. It's not very. So the libsignal implementation is in Rust. That is another interesting part, right? So if one is trying to understand Rust, learn Rust, this is a great resource to start off. What are we aiming today? This is a slightly ambitious aim, but let's try to do this anyway. There are 2 important sub-protocols of Signal protocol. One is the contact discovery protocol. This is called CDS, contact discovery service. And second thing is the double ratchet protocol. Double ratchet is very popular. Many people kind of know it because of end-to-end encryption, but there are a lot of other secrets that the protocol, the entire protocol, Signal protocol, has to manage in order to get these things going, right? There are many moving parts. It's a complex piece. There are many different moving parts, and these are the only 2 moving parts that we'll be looking at today. And it's pretty complex, and it's very interesting. So the information that I'm going to present here is, where does it come from? It's derived from looking at the source code libsignal implementation of Rust, which is open source, and then looking at their blogs, studying some of the research papers that they use to implement these things. So there are many different sources, right? Okay, so this is the very oversimplified system design for Signal for today's session, for the next 20 minutes or 30 minutes or so. Because we want to talk about contact discovery and messaging, right? There are two servers. One is the contact discovery service, which makes use of Intel SGX extensions. And the other is the one that stores encrypted messages, the one on the left side, right side. So IP addresses are also open. These IP addresses are baked into the software, right? They don't come from configuration files or things like that. So if you open libsignal and Signal's Java server code, these IP addresses are baked into the software. So it's like that. In this diagram, if I can call it as an architectural diagram, there are 3 or 4 arrows. The others are boxes that we are interested in today. The first is the registration, how a Signal app registers itself with one of those servers. Then there are 2 entities. We'll talk about 2 users who want to communicate, Alex and Bob. So if Alex wants to send a message to Bob, how does Alex discover Bob? And then once something about Bob is discovered, how does Alex talk to Bob, right? Because this has to be cryptographically secure, end-to-end encrypted. So we can imagine that a whole lot of cryptographic material should come from the server to Alex's app. So I've shown 2 apps, one on the left-hand side and one on the right side. And then the first message that Alex sends to Bob is the pre-key signal message. These are terminologies that Signal has, so I just use. And DynamoDB is the database that sits in between these 2 servers. This is a simplified architecture, but it is accurate, right? So this is the slide that captures whole of Signal's philosophy. This is something that I didn't know before I started looking at Signal and started looking at it seriously. Signal doesn't trust its own servers. This is something contrary to all the rest of the other software that is in this world, runs in this world, right? Everyone trusts their servers. Signal doesn't trust its servers. So it always assumes that servers may be compromised. So despite such attacks that can happen on the server and a compromised server, is there a way to achieve privacy and security when 2 entities are communicating? This is a problem, this is a challenge. This is an engineering challenge that Signal solves the problem, attempts to solve. So the solutions are not easy and the solutions are not direct. They have evolved over a period of time. And if you follow Signal's history, there are a lot of criticisms against Signal. They don't do things right and things like that. But it's hard to get, these are like conflicting kind of requirements, right? I don't trust my own servers, and yet I want to give as much privacy and security to my users. So the only trusted entities here are the mobile phones, the 2 devices that the 2 end users are using. So this is the threat model. The threat model for Signal is that servers may be compromised, and yet we want to be able to work, right? So you can interrupt me if you have any questions, urgent questions, and otherwise we can. So I'll try to discuss the entire problem in terms of just a couple of messages that Alex wants to send to Bob, right? So Bob is the receiver, Alex is the sender, and then the protocol doesn't assume that Signal is not an interactive protocol, let's put it that way. So two entities need not be online, like TLS 1.3. So client and server have to be, both have to be online. The client sends a client hello message to the server, server has to respond, right? So it's an interactive agreement that they reach to. In Signal, that's not the case. Alex may discover Bob, send a message, and God only knows when Bob might respond. Bob may be offline for arbitrary amount of time, right? So this is something that we should keep in mind. And despite that, just think about this. Alex wants to send a message to Bob, and Bob is offline, but it has to be end-to-end encrypted. In most of the other talks, there were a couple of other talks in the morning I attended. So they were talking about symmetric key cryptography. So if you talk about, for example, symmetric key cryptography, both ends have to have the keys to one encrypts and another decrypts with the same key. But then Bob is offline now. Alex is sending the first message. How does Bob figure out what is the decryption key, right? This is the bootstrapping problem the double ratchets try to solve. So let's try to, so what should happen ideally? So when Alex wants to send a message to Bob, obviously the sender has to first get hold of, this has to be a symmetric key. Let's think about it that way. Let's think about it logically. We need to have public key cryptography. We need to have asymmetric key cryptography to solve this problem because Bob is offline. But Bob must have published his public keys to Signal server, right? And then when Alex discovers Bob, what Alex discovers is the public keys of Bob. There is no symmetric key. Then, logically speaking, Alex has to do something with these public keys and derive a key to encrypt his messages. Right. That solves Alex's side of the problem. But now what should happen to Bob? So when Bob comes online, he should be able to derive the same keys that Alex has derived, right? Because the encryption and decryption happens with the same key. Alex derived those keys by looking at the public information that Bob has published to Signal server. So Bob would have published it to this right-hand side server. So registration is an important step in Signal app, even in WhatsApp for that matter. WhatsApp also follows the same protocol as far as, if you look at their white papers, WhatsApp's white paper, which is available on their website, you will see that they use the same terminology, pre-keys, double ratchet, and the credit goes to Signal Foundation. And there are multiple blogs wherein Signal and WhatsApp work together, so you can read all that online. So these keys that Alex has to discover, they are called as pre-keys, just because those are the keys that Bob has to publish prior to anything else. So all of us who uses Signal, behind the scene, our app has published a bunch of pre-keys to the server. And remember, the server may be compromised. So what we publish on the server may not act kind, right? That itself may be an attacker. So there is this problem. So how does Alex discover Bob's pre-keys? You need phone number. As it stands today, Signal needs your phone number to discover. So many people don't like this. They say, oh, Signal doesn't do it right and all that stuff. So Signal doesn't claim today to implement anonymity of the user. It only aims to provide privacy, not anonymity. So your phone number is required today to discover you on Signal. So is on WhatsApp. But what does Signal do? Once you are discovered, the user is identified by other identities. They are called as ACIs, account identifiers, or PNI, phone number identifiers. Signal needs our phone number only to discover another contact. Beyond that, Signal doesn't store the contact list. It doesn't store our social graph on its server. How does it do that? We'll see in the next few things. So once it finds out the pre-keys and all that, there are some cryptographic operations. Hopefully, we'll try to look at it today, and then sends a pre-key message. That's all we try to understand today. Right, let me just skip. So initializing the session is an interesting protocol. History is like, the research for this happened in academia since 1970s, right? So these are some of the names. There are references. You can go look up who they are, what do they do. These are people who are from academia. So the seed of these ideas came from universities. And Signal even today works very closely with universities and other research labs when it comes to, they work with sharp cryptographers. And one of the algorithms that we will skip over today was discovered by Emil Stefanov, who was a Berkeley PhD student who passed away after publishing these papers. So this is a good way to remember him. Okay, so let's look at the registration API. As I said, this is what I have put up on the server is a gigantic slide. I have tried to reduce the number of slides here, and then I may skip. I'm sorry about that, but then time isn't enough. So this is the registration API, copied directly from the Java server of Signal. Signal server is written in Java. Signal library is written in Rust. And Android client is written in Kotlin. And on iOS, it's written using Swift. And we have Signal also running on the desktop that is written in TypeScript, right? So this is a Java piece of code. All that I want to highlight here is that this is not gaudy, right? So I hope this attracts due attention. There are only a few things that are important during registration. So, for example, the application, as a part of the registration response, the ACIs and PNIs I was talking about, the unique identifiers of the registered client, they are generated on the server. So, they are cryptographic values, they are random values. They are UUIDs, essentially, 128-bit numbers that the server generates. So when my client registers with the Signal server gives me two identifiers, ACI and PNI. They're randomly generated. And then, of course, there are a bunch of things. For example, the registration request, when it goes from the app, Android app, to the server, a lot of key material is generated on the Android device also, Android or iOS, on the mobile device. So some of those are here, right? Some of the keys and those things are produced by the client. Identifiers are given by the server. So this tries to capture what is, so it's a nested structure. If you look at the Java declaration, there are a couple of structures which are embedded within the outer structure. So this tries to capture that. Or there are other APIs. So this API these are all HTTP requests that go from the client to the server. So this one is the registration API with which the application can give many of its attributes. There is another API called VI accounts, V1 accounts. With accounts also, we can go and update our settings, and then some of these attributes get updated. So this is a registration thing. So we'll quickly move on to the phone number discovery, and then hopefully Ratchets as quickly as possible. So Signal allows us, gives us, this is a screenshot on my Android phone. So Signal gives us, if you have gone to the settings of Signal, it gives us facility, it gives us it has a way for us to control whether I should be discoverable or who can see my phone numbers, right? So if I'm not already there in somebody's contact list, they'll not be able to, even if I send them a message, they'll not be able to see my phone number. right? So that is one way to hide my phone number. There is another second one, who can find my number? So this is discoverability. I can go to settings, signal setting, and then say, nobody should be able to discover me. In that case, it becomes extremely difficult. That's why when you choose the nobody option, default is everyone. Signal would have everybody as the default option. If you choose nobody, Signal puts up a message box saying that, look, you're getting into the danger zone, you're getting into the isolated mode wherein nobody will be able to discover you, right? So some people would like to do this. Then the question as to how will they be discovered? If I go and say that nobody should be able to discover me, how would I allow others to communicate with me? Signal has other things like QR code, usernames, right? We will not be talking about that today. But today will be phone numbers, discovering by phone numbers. Okay, so this is difficult to implement. It's on other servers. If I were to use traditional techniques, it's a much easier way, right? I store the phone numbers and then I make a search, database search. But now Signal doesn't want to know anything about your contact list. So when I first register with Signal, my contact list has to go to the server, right? My contact list goes to the server, and then I may be asking, tell me who in my contact use Signal, so I can send them a message. Let's say Alex wants to, Alex's contact list is sent to the server. Now, Bob might have set on his phone that he should not be discovered, in which case Alex should not be able to discover him. But Alex doesn't know. So Alex's contact list, Bob may be in Alex's contact list, but yet Bob may not want to be discovered. So Alex will not know. This is a way to know whether, this is a security hole, right? If I add you to my contact list, and then I get to know that you use Signal, that's a privacy breach. So Signal goes to that extent, saying that if you don't want others to know that you are using Signal, you can block others from seeing you, block being discovered. So this is this option. So the entire contact list and entire database of phone numbers and ACIs and PNIs, it has to be protected. It cannot be in a database where when servers are compromised, somebody will get to see. It has to be in memory. So all the complete implementation of this contact discovery happens in memory. It's not on servers. It's not on any database. It's not on any external device. It's on the server. The technology that is used is SGX. Previously, I was asking to the previous speaker, I was asking a question because I wanted to understand something about SGX. So the blog mentions, Signal's blog mentions that at peak time, at some time, so this contact discovery has gone through two phases, version 1, version 2. What we are using RAM in Signal is version 2. Version 1 was using a slightly inefficient algorithm. Therefore, their blog says that at some peak time, they were using 600 servers. And Signal is for free, not like WhatsApp, right? So unlike WhatsApp, Signal is free, it doesn't store your contacts, it doesn't need your social graph, and yet they incur costs. 600 servers, can you imagine that? And with a slight change in the algorithm, I shouldn't say slight, with a new implementation of a different algorithm that was proposed by this person, Emil Stefano. It's called PathORAM. With that change in the algorithm, right, from 600 servers, it got reduced to 10 servers. That's where I think research and engineering research helps. It's not just about anything else, you know. Engineering research is important. And adoption of that engineering is also important. So, and as they say, the cost is also high. Somewhere else I have mentioned that. So, the contact discovery, this is for, since I come from a university, I like to highlight these things. These are the research ideas, a long history of research where if you are interested, you can take a look. Basically, the hardware support that Signal requires for contact discovery, the left-hand side server, not even on the right-hand side, the left-hand side server that in our initial threat model diagram, uses Intel's, it requires Intel's SGX enclaves to be present. So all the enclaves give you all the encryption and protection of pages and stuff like that. So it's interesting. So this, if I can capture it in a diagram, this is the diagram that I would like to show. This implementation itself is a project, separate project on GitHub. If you go to Signal's GitHub repository, Contact Discovery version 2 is a new project. And this is the final blocks and arrows kind of architecture. So there are two parts in an Intel's enclave. There are two parts to the code that we write. One is the one is the trusted part, another is the untrusted part. So all the search happens, contacts are stored as a tree. We can say that it's a binary tree, but the nodes of the tree are not just single phone numbers, they are called buckets. That bucket stores a bunch of blocks, right? I have some calculations here drawn from the source code. So each bucket, important to note that each block stores around 24 records, 24 user records. What are these user records? The phone number of the user, the ACI, the PNI. Only ACI is enough, but sometimes PNI is also required. Those are the details that we will not go today. So these are the records that are stored in this binary tree that I showed here, right? And the search over the binary tree, this algorithm, the contact discovery algorithm is so clever that one of the things that happens with enclaves, if implementers are not careful, is that if you just assume that encryption gives us safety, it's not so, because even if my data is encrypted and stored as a binary tree, if I search for, let's say if I search for an entity here, let's say the 10th node, every time I search for the 10th node, the access pattern is going to be the same, right? The access pattern is going to be 15, 7, 11, 10, or 9, 10. So this is a side channel attack. An observer, remember, in Signal, even the server may be compromised. The data center may be a threat to the Signal server. Signal servers run on AWS. Amazon itself may be a threat actor for Signal. So since Signal doesn't trust even the data center, it trusts only the CPU. The trust has to be placed somewhere. Only the CPU's enclaves are trusted. So what should happen is, the moment I search for a contact, this path, right? The moment there is a search, this tree has to be rewritten. This tree has to modify. The cleverness of the algorithm is that the moment I read this path, the data in this path gets written to other path. In other words, they get shuffled. Let's just put it in a very simple term. Entities, the data gets shuffled in this tree. So what happens is, next time I search for 10, it doesn't come this path. It goes via a different path. So every time I search for a phone number, the search path is going to be different. So the data is not just encrypted by enclave, the access pattern is also different, right? So this ensures that there are no side channel attacks. Observers cannot see which data is repeatedly accessed. So this is a very clever thing. I haven't put the algorithm here because I removed it. I had the algorithm. I think it's available on the slide deck, the gigantic slide deck, which is on the site. So this is the contact discovery cleverness. The second part is the ratchet part, where end-to-end encryption has to be secure. I hope I'm maintaining time. You have to tell me, you have to prompt me when I have to. 5:44 it is, right? In short, just so that we can go to the forward secrecy part, so Alex discovers Bob. So how does Alex discover Bob? With this algorithm, right? Somewhere on the 10th node, Bob's phone number exists, and Alex has discovered. And then Alex wants to send a message to Bob. So we just mentioned that we need asymmetric key cryptography for that. So this is the only slide where I have a very simple math, so bear with me. So what's the basic idea? The picture, so the idea is that this key, the private key of Alex, has to be somehow combined with the public key of Bob, because Bob has published his public key. And then this operation, this mathematical operation, it is a function. It has to give the same value. When I combine, mathematical functions are like that, right? If the arguments are the same, the result is the same. So Bob's public key, when mixed with Alex's private key, by the way, these keys are 256-bit numbers, 32 bytes, right? So this, okay, Signal doesn't use RSA. RSA is broken, right? Although many embedded systems devices still use RSA, the rest of the world has moved to elliptic curve cryptography. Signal uses ECDH, elliptic curve Diffie-Hellman. Then what happens? Symmetrically, after Bob comes online, so here you see Alex would have combined his private key with Bob's public key. Now this is mathematically equivalent to combining Bob's private key with Alex's public key. They're symmetric, right? So this is the magic of Diffie-Hellman. How does it work? I will show a very simple exponentiation of mathematical expression, right? This is the essence. This is not highly accurate, but this shows what's happening behind the scene, right? So assume that Alex's private key is 5, and assume that your base is 9. So both have agreed on a base called 9. RFCs define what the base number should be. Let's say both have agreed on a number called 9, right? And if Alex's private key is 5, when you raise 9 to the power 5, okay? And if, what is the public key? Public key is, well, I have a typo, I suppose. So let's say Alex's secret key, private key is 6, therefore 9 to the power 6 is his public key. Okay? So I have taken small numbers so that you can run this in your Python terminal also. You can just type a Python expression. Then if Bob's private key is 5, his public key will be this, 9 to the power 5. So this is a public key, this is a private key. These are small numbers now, but imagine 256-bit numbers, 32 bytes. So if I know Bob's public key, right, private key, so 9 to the power 5 to the power 6 will be same as 9 to the power 6 to the power 5. So, but we cannot exchange public keys, private keys, we can only exchange our public keys, right? So, what happens is 9 to the power 5 is Bob's public key, right? Here is 9 to the power 5. 6 is Alex's private key. So, when you take 9 to 5 to 6, this is equal to 9 to the power 6, which is Alex's public key, 9 to the power 6 raised to Alex's private key. So both can hold on to their private keys. All that they need to know is the other guy's public key. They exchange public keys, they come to a shared secret. Right? This is the beauty of a simple math. So I've shown the complete, shared secret they come to. But then what happens is, it's a good engineering practice not to use this shared secret right away. It has to be random. It has to look pseudo-random. It has to look more random than just this number, taking to the power. So there are some tricks, cryptographic tricks. So these are called HMACs and HKDFs, key derivation functions. You run them through this shared secret. Alex derives through the KDFs, and then he gets his key. Okay, the rest of the bits are not important here. So basically, that is the key material that Alex derives. By symmetry, by a symmetric argument, when Bob comes online, he will be doing the same thing. He'll come with the ends up with the same shared secret and ends up with the same keys. So this is the crux of end-to-end encryption. Now, the missing piece in this is, Alex is the first one to initiate the conversation, right? Bob doesn't know Alex's public key. So what should happen? Alex discovers Bob using CDS. When he discovers, he also gets to know his public key. So Alex will raise Bob's public key to his private key and comes to a shared secret. And in the first message that Alex sends, he has to put his public key. That's it, right? He has to, in the first signal message that Alex sends to Bob, he puts his public key. So Bob gets to see the first message and the public key. So there is a small twist. So in the morning session, somebody was talking about PQ, Post-Quantum Cryptographic Algorithm. Signal has moved to a post-quantum secure posture. So it uses MLChem, and these are the researchers who proposed MLChem and won that competition that NIST had succeeded. Again, academia, right? Most of them are from universities, others are PhDs from universities who work in industries. Mathematicians and cryptographers. So this trick is, DH is the function, right? So if you remember here, DH is the function. So this algorithm is called DH, but Signal makes an extension to it. So it's called XDH, extended Diffie-Hellman, and now PQ because that's a marketing thing, right? So post-quantum extended Diffie-Hellman. So it does this and then ends up with the post-quantum secure. So even with quantum computers, you will not be able to break some of the cryptographic primitives that Signal uses, right? So with this, now comes the rest of it. Now comes, once they have the shared secrets, I'll just quickly go through it, sending the first message. So through this KDF, Alex derives the first key. And then I'll just scroll through the other things. So this is what happens. Alex will end up with a key, with the first key, and for the first message, generate the ciphertext, encrypted text, send it. Generate the second key. So each message in Signal is encrypted by a new key. So this is where what is called the forward secrecy comes. For example, forward secrecy is all about this, the same diagram. Forward secrecy is that when you use one key and hash it to derive the next key, each message is encrypted by a separate key, right? These are all different keys, but they are produced by the previous key. So if at any point in time, if my phone is compromised, if somebody gets to know the key here, SE key 1, SE key I, for example, will they be able to figure out the previous keys? No, because this is a hash function. The earlier key would have gone through a hash function to generate ith key. So they won't be able to go back in the hash function. Hash functions are one-way functions. If I know the hashed value, like SHA-256 and all that stuff, you know that. So with the hash value, I will not be able to, from the image, I will not be able to find the image, right? There is no pre-image. So this is the forward secrecy stuff that Signal claims. Even if your phone is compromised, all your other messages are secure. They cannot be decrypted because those keys cannot be recovered by knowing the current key. Obviously, after the ith message, I plus 1, I plus second message, that can be decrypted by the malware, by the attacker who has gotten hold of my phone's secret key. Right? So forward secrecy is an important property that Signal and WhatsApp by definition provide. There is another, so when will this heal? If my phone was compromised and if some attacker was able to get the key, will he be indefinitely, will the attacker be able to indefinitely access my messages and decrypt my messages? Not so. What should happen is Bob should respond to my message. When Bob responds to my message, he would introduce a new randomness, which would be used to, I show it in this diagram. When Bob sends a new message to me, because you see here, every time I send a message, there is this DH operation, right? When Alex sends a message, Alex generates a new elliptic curve key, mixes with Bob's public key. So for every message, for every new session, this happens. When Bob sends a message, Bob would have done the same thing. He would have generated a new key for himself. So in this diagram, when I receive Bob's message, I would have some new randomness coming to me. So this ensures that with that randomness, my new keys, symmetric keys, will have freshness. So what happens is, even if I am compromised at this point, at somewhere at this point, if Bob responds to me, Bob responds to Alex at some point, they will heal their sessions again. So from then onwards, again, they'll be okay. So interaction is the key. If one is offline and one doesn't respond to messages, end-to-end encryption will not help. If our keys are compromised, that violates forward secrecy. That violates it's called post-compromise security, right? PCS. So PCS comes with interaction. Two agents must continuously interact, then they can derive new randomness and newer keys. Right. So I'll just stop there because I'm coming to the end of the time. So there are many other interesting things in Signal which we haven't. Anonymous credentials, that's without phone number. How do I make, if Bob doesn't want to share phone number with anybody, his phone number, how does he make others see it? So he can do that with usernames. So anonymous credentials in zero knowledge proofs. Signal already has that facility. If you go to your settings there is a provision to give username. And then you can generate a QR code which you can share, either the username or the QR code. Then people, so that will be a very, very private. So how do users find your QR code or something? You privately meet. See, generally activists or some of these people, they meet in person, exchange their QR code or exchange the username. They won't even share their phone numbers, right? Signal is meant to be used in that level, that kind of security. The engineering is interesting. The math part of it is interesting. So then this we have just seen how Alex talks to Bob and Bob talks to Alex. So groups, how do I make a group and how do I talk to the group? Each group member, Signal is designed in such a way that if you are in a group, if I send to one of the group members, other group members will not know because I will be using different keys with each group member, right? So if I have 100 people in my group, I'll have 100 different keys for each one of them. And as you can imagine, each time I send a new message, new keys will be generated for each one of them. The symmetric key ratchet will be progressing that way. So that in itself is interesting. And then now there is triple ratchet. Beyond the double ratchet, there is a triple ratchet because of post-quantum security, right? That's not yet implemented. It's in the making. The paper has been published. It's a very interesting paper out there. And a part of the implementation is already available on GitHub. Interested people can see. Thank you. And these are the slide. Yeah, slide has all these references. Every word that I have uttered comes from one of these papers or the blog posts or articles that Signal and Signal's researchers have written. You can all look up. Thank you. if you have any questions, I'll try to see if I can answer.
Hi, sir. So when you mentioned that post-compromise, it's still possible for the encrypted communication to heal.
Can you, this room, yeah, I heard other speakers say that, they can't hear. I can.
Oh, I'm out. Okay, it should be better. So when you said post-compromise, it's possible to heal the encrypted communication. Does that mean it repeats a Diffie-Hellman after a certain interval?
Does that mean?
Does that mean the two clients repeat a Diffie-Hellman after a certain interval or for every message?
I honestly can't hear you.
Oh, you can't?
So, can you make it a little slower? Yeah, maybe come here or, yeah.
Yeah, so
after so the keys are compromised, then?
Then you said it's possible for it to heal even if the attacker has previous hashes.
It's possible
the healing. So the attacker could have the ith hash, and you said that normally you could derive all subsequent hashes, and that's how normal communication would go on.
Right.
But you said even in that case, there is a measure
post-compromise security. Yeah.
So that is, you said it adds randomness.
Right.
So is that just by doing a Diffie-Hellman again, or is there something else?
Yes, you are right. That does every step. Every time Alex sends a message to Bob, there is a asymmetric ratchet, Diffie-Hellman ratchet runs. Every time Bob responds to Alex, he would have generated a new elliptic curve private key pair. So he would have put that randomness into his. So that public key comes in that signal message. So Alex takes it, and then builds the DH ratchet again. So it's in this diagram. It's in this diagram, and it's in this diagram, right? And this is the diagram that reads a little bit of elaboration. This is how they will grow. You can see I have just, to show that they are symmetric, I have taken pains to draw them so. Bob's version of sending chain and receiving chain. Yes, there is a freshness because of the elliptic curve Diffie-Hellman keys that are produced by Alex and Bob.
Okay, so essentially they do Diffie-Hellman for every message.
Right.
Okay.
For each message exchange. So I send a message to you. When you send a message, you do a Diffie-Hellman. Again, I reply to that, I do a Diffie-Hellman.
I see.
Right.
Because in situations like TLS, you only do Diffie-Hellman once.
Oh, you already know it. Yeah, nice. So in TLS, that's why. TLS is like an interactive thing, right?
Yeah.
So you do once Diffie-Hellman, you derive the keys, and then you are done. So by the end of client hello and server hello, you are done.
Yeah.
Right? That Diffie-Hellman is done. And beyond that, they don't do any more Diffie-Hellman. That's done.
Okay, but in here it's different.
This is different. Okay. This is beyond TLS 1.3. This is with each message that you exchange, there is a Diffie-Hellman ratchet.
I see. Thank you.
Yeah. That's a good question. Thanks. Yeah.
Hi. Am I audible?
Sorry?
Sorry. Am I audible?
Yes.
Yeah. Thank you. Very interesting lecture.
Thank you.
So actually, I'm not in cryptography background, but just I'm curious. Nowadays, you're getting these ads on TV, right? WhatsApp cannot read your messages, something of that sort. So the question is, in all this, can server decrypt the message somehow?
Okay.
Yeah.
So to answer that question, let me just go to the threat model. The threat model shows that since Signal doesn't trust its own servers, servers will not be able to decrypt because the key material is in this mobile phones. Server will not be able to decrypt. No one will be able to decrypt. The AES CBC is that way very secure, that Signal uses. And then keys are also randomly, there is freshness every moment, so therefore brute forcing will not help there. The server, on the other hand, can play tricks. It cannot. It may not forward the message. I send a message to you. you come online, server will not give you that message. Your phone contacts the server, says, hey, is there any message? Server says, no, I don't have any. That can happen, right? So beyond that, there is no other thing that server can know. These are stored encrypted on the server. Have I answered your question?
Thank you.
Yeah.
But the government says, right, they are able to decrypt messages, right?
Sorry?
Government is able to decrypt the
Yeah,
words.
so this is, okay, the regulatory thing. With Signal never has yielded to any. So this is one of the reasons. See, especially this extreme step came from Signal after Snowden. I don't want to make politically incorrect statements in this talk. So therefore I have been careful. I had some slides. I removed them, and the only slide that I had, which perhaps is politically incorrect, is this slide, naming countries. But this especially happened after Snowden revelation, that NSA has backdoored many servers. So Signal is like now, even if NSA comes there and their threat model is such that server doesn't know anything, right? So regulated entities, whether they are governments or anyone, they cannot do anything with Signal, right? So that's, I have removed a few slides which I thought may not be appropriate. They used to, in these countries where I had no Signal, right? In these countries, Signal used to have a mechanism, it's called domain fronting. Using domain fronting, you can hide your domain. So instead of connecting to signal.org, it would connect to abc.xyz, and abc.xyz will be forwarding the request to signal.org. So in a country that bans Signal, and in a country which looks at all the traffic, it would look like the traffic is going to abc.xyz, but it would end up in Signal. Then, because of regulation, and what used to happen was this domain fronting was running on Google's cloud and Amazon cloud. And these are commercial entities, right? So they said they will not support this. They will not support domain fronting for Signal. So Signal had to take down all those servers. So therefore, since 2018, Signal has no support for those things in these countries. So there are some blog posts in Signal blogs where they say, okay, run a proxy, help us running a proxy, in these countries, and then, yeah, it's difficult with regulated entities. But with the server encryption, entities cannot do anything. With everything else, they can have control. Yeah.
Hello?
Yeah.
In Signal, does it have a root cryptographic material, or is it generated every time? And the second question is, when you log in from another device, right, they'll not have access to the same cryptographic material.
No.
How would they be authenticated?
Linked devices, right?
Yeah.
You mean to say either a linked device,
Linked device, or maybe you...
another phone.
Yeah, exactly.
With a different number. So no, with every device that you have, Signal has fresh. There is nothing shared across devices. It cannot be.
I mean, in terms of linked identities, if you have the same application...
Okay, that's a good question. So, yeah, I get what you are going. Okay, ACI is shared. So that's the reason there are two identities. One ACI, another PNI. PNI is the phone number identity. It's a unique UUID per phone number. ACI can be shared. So I have a Signal account. I can have two different phones, one iOS, one Android, which runs WhatsApp, but I can be using the same account.
So the key material will be shared via QR
No,
code?
the ACI is shared. ACI is not any key material. ACI is an identifier. It's like name, Devi Prasad. That's it. ACI is a UUID, unique UUID. Corresponding to that ACI, I didn't elaborate there. If you look at these diagrams very carefully, because it's too much to talk about these things at 5 o'clock to a crowd which is already tired. See here, there is a ACI identity key, right? And then there is ACI signed pre-key. This is not one key material. Corresponding to an ACI, there are different key materials. So devices, this is a device, this is on the device. Can you see that? So each device will have its own key material corresponding to this ACI. Right?
The same message will be different ciphertext for different devices.
Yes, you are right. That's one of the reasons why if you use multiple devices, you will see some messages getting lost. You would have deleted them, but they show up there, right? It's a different subprotocol. Device control. Yeah, there is a lot going on here. There is a lot of cryptographic stuff going on there. Yeah. Okay, if there is no other question, I'll stop. Thank you very much. Thanks for your patience. Yeah.